now I will go to the fourth lecture of week 10 of this course, and in this lecture I will talk about a slightly different way to visualize crystal structures, that is through space filling polyhedra, and then I will talk about alloys. Okay. I will talk about alloys, what are the different kinds of alloys you can form, and just show you how you can get many different kinds of alloys. Okay. So, week 10 lecture 4 will be space filling polyhedra and alloys. So, now let's visualize some structures as space filling polyhedra. I'll just show this through an example. Okay. The example I will take is the sodium chloride structure. Okay. So, we will start with the sodium chloride structure. Okay. Here in a sodium chloride structure, okay, you take the, let me show the chloride ions as forming the close pact and the sodium ions as occupying the octahedral voids. So, if you take sodium chloride, okay, I will show the chloride as forming a close pact and the sodium as occupying the octahedral voids. Okay. So, what you will have is I want to show. So, these are the chloride ions which are occupying the close pact structure, which are forming a close pact structure, cubic close pact. So, just to show what the cubes look like, they look like this. And there will be a few more chloride ions, there will be at the centers of each of the faces. So, this is a close packed structure formed by the chloride ions, and now the sodium ions are going to occupy the octahedral voids. Now, let me show the one octahedral void in the center first. Okay. So, at the center of the crystal there is an octahedral void where the sodium ion is enclosed. I will start with this void and then I will go to the other voids, other sodium atoms. So, in the idea of space filling octahedra, you look at coordination polyhedra around cation. Okay. So, the focus is on the cation and look at the coordination polyhedra around the cation. So, let us look at the cation right in the center. Okay. Let me show the other cations, but now I will first focus on the cation in the center. So, now the cation right at the center, if I look at its the coordination polyhedra, that means you look at the nearest, the atoms that are closest to it are these 6 chloride ions. So, these are the ions that are closest to this. Okay. So, these 6 ions are closest to the center sodium ion, and now you can make a polyhedron. Okay. So, we will just see that this will form you can clearly see what this will form. This will form an octahedron. So, the coordination polyhedra is an octahedron. Okay. So, clearly it is an octahedron that is formed around this, and let me erase these lines that are inside just for clarity. Okay. And okay, so this is what the coordination polyhedron, this is what this octahedron will look like. Okay. And we will just shade it just to emphasize. So, this octahedron will contain only the sodium atom at the center and no other atom. No other atom will be inside this octahedron. Okay. So, this octahedron is a coordination polyhedron for this sodium atom. So, now what you can do is you can do this for all the other atoms. Okay. For example, you could do it for this sodium atom. Okay. Now, and again you will see that you will have another octahedron. In this case, you have an atom here. I have to extend the structure to this side and put an atom here. I have one that is in the center, and I will have one that is in the back plane. Another one that is here. This is in the plane on the back, and then yeah. So, these are the six nearest neighbor chloride nearest neighbor sodium ions, and you can again see that they will form this octahedron. And again, if I shade it, you can see this coordination octahedron. Okay. There is a little bit of smudging that happened here, but that is just due to this program. Okay. Now, you can do the same for all the sodium ions, and you can make similarly you can make coordination polyhedra. What I mean, I'll emphasize this point by looking at this sodium ion just to show a point. Okay. Now, if you look at the coordination, if you look at the nearest neighbors, so there is one on this face, one here, and then one similar one will be located here. There is one on the back face, and one here and one here. Okay. Now, what you see is that the coordination polyhedra will share this edge. So, these two coordination polyhedra will share the same edge. Okay. So, you can see that in this octahedron here I will not share it, but I will just emphasize that there is one edge which is shared between the two octahedrons. Similarly, here also there will be one edge that is shared between the two octahedrons. Okay. So, you can really look at this structure as a set of polyhedra as you can do this for all the sodium ions, and so the whole structure will just look like a set of octahedra, edge sharing octahedra. Okay. So, this is just a way to visualize the structure that emphasizes the coordination. Okay. So, this emphasizes coordination of ions. Okay. And additionally, there are points that relate to how these octahedron touch, how these octahedron are connected with each other. In this case, there is a side sharing octahedron. You can do the same. Let us take the case of zinc blende. Now, in zinc blende, okay, let me put the sulfide ions at the cubic close packed structure, and now I will put the zinc ions. As before, I will show this in. So, these are the sulfide ions. That are forming a close packed structure, cubic close packed. And now the zinc ions will occupy the tetrahedral voids, that will there will be one here, one that is along this diagonal. So, that will be somewhere here, located here. This is actually along this body diagonal, and a fourth one will be located close to this, along this body diagonal. So, that will be located 1/4 way along this. Okay. Now, let us look at this particular zinc ion. Okay. Now, this is closest to 4 other it is closest to 4 other sulfide ions, and those are and one in the front face. I did not show. This is in the, it is closest to these 4. Okay. And now you can see that the coordination polyhedra will be a tetrahedron. Okay. So, it will look like this. Okay. And now if you take this neighboring, this other zinc ion. Now, this the polyhedra for this, okay, so these are the 4 and this one in the back face. These are the 4 nearest neighbors, and now you can see that you get another tetrahedron. Now, in this case the 2 tetrahedrons only share one corner. Okay, so is an edge sharing tetrahedron. Okay, so now the structure looks like a set of corner sharing tetrahedron, and you can extend both these octahedron and tetrahedron to fill the entire space. Okay, so this is how you visualize structures as in terms of space filling polyhedra. Now, I said that there are 2 common coordinations. Okay, so octahedra is 6 coordinated and tetrahedron is 4 coordinated. Okay. So, if your cation is coordinated to 4 other anions, then usually there is tetrahedron, and there is octahedron if it is coordinated to 6. Okay. Now, you can sometimes the coordination, sometimes you can have things like trigonal bipyramidal, middle. Sometimes the coordination number is just 2, okay, 2 nearest and plus 4 next to nearest. Okay, this is in the case of the distorted octahedral void, which we saw in the case of BCC. Okay, so that is also possible. Okay, so there are other possibilities, but the most common ones are the tetrahedron and octahedron. Okay, and it is in these cases that we usually show the structure in terms of coordination polyhedra. Okay, now that's about what I want to say about coordination polyhedra. And now let me get to the topic of alloys, and let's start with the example of copper zinc alloy. So, let us take copper zinc alloy. Okay, and now the point is that now both copper and zinc, they are FCC. Okay, and now you can sort of see what will happen if you have a combination of copper and zinc. Okay, and they have very similar sizes, ionic size. Okay, zinc is 2 plus and copper is 1 plus. Okay, but I mean copper can be either plus 1 or plus 2, but basically they have very similar size of ions. And now what can happen? Let us take one example of perfectly disordered alloy. Okay, so here you can have a cubic close packed structure. Okay, I have a cubic close packed structure, but each and every site here is actually is actually partially occupied either by copper or zinc. Okay. So, each site can have either a copper or a zinc, okay, and there is no it is perfectly disordered. Okay. That means you can have some copper, some zinc, and there is no you cannot really tell which is which. And okay. So, here you have a case of a completely disordered alloy. So, alloys are and this is typically the case for alloys. Okay. So, they are perfectly disordered. Okay. And it looks like CCP, okay, cubic close packed, okay, with partial occupancies of copper and zinc. Okay. So, this is very typical of alloys, and if the size of the two if the size of the two species is very similar, okay, then yes, you will get similar you may get something like this. Now, is this the only possibility? Is this the only possibility? Now let us say you have a large amount of copper. Okay, you have copper, which is 1 minus delta, and zinc. You do not have 1:1. Okay, you have much more of copper and much less of zinc. Delta is very small. Delta is much less than 1. Okay. Then what are the possibilities that can take place? Okay. So, you can get alloys with different structure, okay, but also you can get intermetallic compounds. Okay. So, what is meant by intermetallic compounds is basically some sort of for example, if you get one example, you might get a Cu4Zn, okay, and you might get some sort of repeating unit of this unit, okay, showing up in your structure. Okay. So, a large part of the structure might just be repeating units of some structures such as Cu4Zn or something, okay, and it might not be a simple FCC in that case. Okay. You could get multi-phase behavior, more than one phase. You could get phase segregation. That means in some region you only have copper and some region you only have zinc. Essentially, the number of possibilities become very large. Okay. So, you can get many different structures. Now let us look at the copper zinc system, and let us look at some of the other possibilities that you can have. Okay. So, this I will just list some of them. So, alpha phase is what we had earlier. So, CCP with disorder. So, this is for the copper zinc system, and of course, this is also seen for several other alloys. Okay. Disorder, that means you do not know, there is no ordering the positions of copper and zinc. I mean, they are all in the CCP, but each site, okay, disorder in sites. So, each site can be either copper or zinc. So, that is the phase that we talked about. Okay. But now people have also observed something called a beta phase, okay, where essentially you have one of the ions forming a cube, simple cube, and the other at the body center. Okay. So, you can have something like this. So, this is a body centered. So, it is like a BCC lattice. and you can have one or the other. So instead of having an FCC lattice, you have a BCC lattice, with each site being either copper or zinc. Then, but is this all? No, there is a very interesting phase in this system called a gamma phase, okay, which is actually, so in this case there is a new in this gamma phase there is a stoichiometry of Cu5Zn8. Cu5Zn8, okay. So that is 13 atoms, and 4 of these units, okay. So that is total 52 atoms, okay. They form a big unit cell. Okay. So the stoichiometry here is Cu5Zn8, okay, and 4 of these Cu5Zn8 units together form a rather complicated looking unit cell, okay, which is called the gamma phase. Okay. There are other phases that are also possible. There are hexagonal phases. So epsilon and eta, these are hexagonal phases. Okay. So you can see, and all these are found as you vary the composition and as you vary the other external conditions, you find all these several phases. And I do not want to get into too many details of this, but I just want to say that you know, when you form alloys, okay, there are a lot of possibilities, okay, and that is what makes alloys rather interesting, and the hope is that by changing the composition you can get the properties of interest. Okay. Now, I will just conclude this discussion with a rule which is very popular in alloys. It is called the Hume-Rothery rule, and the question is when do alloys form a good substitutional solid solution. Okay, solid solution is another word for alloy. Okay, when I say substitutional solid solution, okay, what I mean is that is something like what we saw in the case of FCC, where you have a close packed array, but some of the copper is substituted by zinc. Okay, there are certain conditions. So the conditions according to the Hume-Rothery rule are the following. These are rules of thumb that help you predict which systems will form good alloys. Okay, so the first condition is that the difference delta r by the radius of the larger species, okay, should be less than 0.15. Okay, so the percentage difference in size, okay, so size should be similar. Okay, so if two atoms have similar size, then they are more likely to form an alloy. Okay, the second condition is that their crystal structures should be similar. Okay, so if they both have a cubic close pact, that is very good, or if they both have hexagonal close pact, that is very good, or if they both have body centered cubic, that is also very good. Of course, their sizes will be different, okay, because they are two different atoms. But you could also imagine that a cubic close pact and a hexagonal close pact could in principle form a solid solution, because as we have seen, cubic close pact and hexagonal close pact are actually quite similar. Then the solvent which is the larger of the one that is present in greater amount. So solvent valency should be less than solute valency. So in the case of copper zinc, okay, if copper is a solvent, okay, and copper is usually taken as +1 and zinc is taken as +2, okay. So copper valency is less than the solute valency, which is the zinc valency. And the fourth one is they should have similar electronegativities. Okay, so systems that satisfy these usually form good solid solutions, and there are several examples of good solid solutions. Okay, so you can have silver zinc, you can have gold zinc, you can have silver cadmium, copper aluminum, okay, aluminum mercury. Okay, there are several others, copper tin, very famous system. Okay, you could also have things like iron. Well, okay, so I'll just stop here. There are several others, but these are the ones that that obey the Hume-Rothery rule and they form good alloys. Okay, so with this I will conclude this lecture, and with this we are almost at the end of this week. So in the last lecture I will just summarize what we did and do some practice questions. But the point I want to make about this particular the contents of this week is that I have tried to show you a lot of structures. I have tried to show you different ways of looking at crystals, okay, in terms of coordination, polyhedra, and close packed with voids, okay, and the idea is of this week is to actually familiarize you with the language that is used in solid state chemistry. Okay, so when you read books on solid state chemistry or you read journal articles, you will often find lot of these terms. Okay, and so I at least wanted you to be familiar with some of these terms, so that it will help you in reading. Okay, but as far as the actual, I mean, I don't expect you to remember all the structures. Okay, I expect you to remember maybe a few structures like zinc blende, wordite, and so on. Okay, just a few structures, but I don't expect you to know at the back of your immediately which material forms which structure. So just if you just focus on the few structures that we have looked at, okay, you will be fine. All right. Okay, so I'll conclude this lecture here, and in the next lecture I'll summarize this week and do some practice problems. Thank you.